then it can make sense. Then it can make sense to essentially have. Oh, there's a there. Then it can make sense to have people essentially to spend the effort to make this. But this is actually spending the effort to make those experiences. Actually, it's expensive, it's complicated. You need to bring the experts in. They have to learn how to, do essentially PowerPoint in 3D to explain step by step how to do a procedure. This is complicated. Also, those things would be things we'd like to be able to just extract, and leverage AI systems to essentially generate those type of instructions. Okay. Very quickly to remind people what's under the hood in a device like the HoloLens, what's all there. So the device is 5 years old at this point, but essentially it's still in many ways the best device out there for some of these type of tasks. In particular, compared to VR devices, video see-through devices, those devices are not applicable in the real world when you're actually a technician that has to solve a problem in the real world, maybe in training scenarios, but definitely not in actual use in a factory, let's say. So there's, of course, a communication camera, but beyond that, there's a number of cameras that are there to track the device, to have continuous 6DoF estimation, so combination of cameras and IMUs. Beyond that, there's a depth camera. Depth camera is used both for reconstructing the 3D context of the environment, kind of out of the box. So if you record a HoloLens session, you can have all of this out of the box. You can build long-term 3D models from that. The depth camera is also used for good quality hand tracking, combination of machine learning, which runs on the embedded AI processor, used for kind of this detailed hand tracking, combination of AI for detection and finding all the fingers and the points of interest, and then switching to geometric optimization to get a fine-grained position of the full articulated hands. Also, gaze is also built in. Standard APIs to, so for Dima, if she wants to know where people are looking, this is kind of captured right away also. And then, of course, also actually a 5-microphone array that's fully calibrated and gives you spatial audio capture here. Okay, and so all of this is possible at the 1 watt power for all of these runtimes using a custom chip that was built. That's how this is actually was all made possible, and then a normal application process. And so some of the application are this kind of interaction and looking at digital content. For that, today, there are better platforms for looking at purely digital content in these kind of settings. However, if you go in the real world, this is the type of platform that you would use, or, phones and other devices. This should come with audio.
We're giving eyes and ears to AI. So the world becomes your prompt and your interface. This is working. These are thoughts happening.
Hey, some scenarios.
Plans populating.
Copilot, when was this last replaced?
Information gathering. Instructions guiding.
To be able to provide
schematics aligning.
Have this device that can really help the person.
People connecting.
Them in task.
Problem solving.
Overlays, things like that. You actually really
Copilot?
need spatial context.
Copilot. Copilot.
This is confidence.
Once you have that, if you
eyes widening.
Whatever device you use, you can,
these are questions.
I just finished Copilot. What's next?
Okay. Let's do that. So also nowadays, a lot of people say like, oh yeah, but indeed you use GPT something with vision. You take a picture, it will look at a picture and will tell you everything that there's to see in the picture. Okay. That's still a difference from actually having a full spatial map of the environment to over time build up to know not only what's in your field of view at that instant when you take the picture, but actually have built a map, a context for the AI for being able to help the person that has like the full environment reconstructed, meaning that, if you ask a question about something that's not directly in view, you can actually get answers. It also means that if you can align it to things like digital twins, IoT sensors, all of those type of things, it also means that you can actually bring that in the context, which otherwise would not be possible. So that's the complementarity of just instantaneously what am I seeing and answering that with these foundation models, but then also with these vision language models, but then also at the same time having a spatial representation and use those same models actually to map representation of not only what you see in front of you, but what's ever been seen by anyone in the space could potentially be integrated in the representation, right? First step for that is being able to localize yourself in the environment. As you see here, just walk around with the device. The device by connecting to the cloud, can essentially be aligned kind of one-to-one to the digital representation of the environment. To do that, you need a map. So how do you build a map? Well, all those devices, just when they function, need to build at least an instantaneous local map of their environment, just to, to be able to provide a mixed reality experience. Well, conceptually, you could move those representations to the cloud, kind of merge them in the cloud, puzzle them back together, and essentially get that representation. So here's a system kind of in action. Here, first person working, their data gets kind of step by step uploaded to the cloud as they're working. And then as we get more people to contribute, this could be both at the same time or at different times, this gets uploaded in the cloud, gets eventually recognized that, hey, they're working in the same environments, gets merged into single representation. This only has to be people. This can also be autonomous agents, like you see here. Eventually, this is just visualization, but essentially this is kind of what happens in the cloud. It all gets merged together. This works at scale. This is a factory in Switzerland. And this was just collected by walking around with, in this case, HoloLens devices, but we could do it with phones also. Here's an example, Microsoft Studio C, essentially captured by just walking around. Here also actually leveraging the depth camera. And so you essentially have a full representation of every piece of furniture and everything in the environment, as you can kind of see here. Okay. More on the academic side, if you're interested in type of things, we've been working with Microsoft, but in the meanwhile also with Meta and other partners to collect a very large collection of data here. So you see the Lamar data set. It comes with, we've aligned all of this to high quality laser scans. So we estimate that we are within a centimeter accurate. The median error is about a centimeter. 99% is within 3-4 centimeters. So actually very useful data with normals, etc., and with ground truth, and with recorded over more than a year of data. Beyond geometry, of course, we want also semantic information in terms of providing grounding for those copilots in the world. This is some work that is connecting essentially through clips, so word embeddings, so word, language, and images that's been extended then to also include geometry. And so at that point, you can essentially ask questions about environments, open set type of questions. As you see here, you can ask about floor, for example, and then what it does, it has pre-processed the whole scene. It has associated clip vectors to every point in the scene. And then when you ask a question, it generates a clip descriptor based on the question, and then correlates that with the whole scene and highlights the most, the most relevant parts of the highest dot product, right? You see, you can ask all different types of questions about specific objects and classes, very specific objects here. There's like one in there. But then also more things like affordances, materials, and all these other type of things you can also ask questions about, like here sitting, for example. Okay. Here's another, of course, we had to do something with NERV. So instead of just having the RGB being predicted at a particular location, you can actually predict the whole clip vector. And then you can, again, do the same type of things and render essentially how relevant a particular thing is to the question. Here's something that directly actually brings together clip and so this open scene work together with segment anything. You bring those two things together, and now you can get essentially instances immediately clustered as instances and ask questions about it, and retrieve the right instance of objects in the scene. Here's an illustration of how, if you bring that then in a system, how this can look like. So here's some experimentations that we've been doing at Microsoft on this. And then essentially this was our previous office in Zurich. And then you can ask questions where particular objects are, and you see kind of the link to the original images that it's run from. Here's then some more explorations. You might recognize Clippy, this kind of not so successful assistant from back in the days at Microsoft. But of course, because we used Clip, OpenAI Clip, to use this, we figured this was a good idea. Some of the execs didn't thought it was that funny.
Plans.
Anyway, so you can ask questions. You're attached to this. There's a map attached to your position, so you're localized within a map. You ask a question. This is voice. I don't have the audio here, but you just ask a question. It gets speech to text, and then essentially highlights a part of the scene or navigates you to the part of the scene that's most relevant to your question. Here's kind of then, this should actually have audio. So,
hi, Copilot. I was tasked to water all plants.
Okay, it's not very loud, the audio.
Could you please tell me how many potted plants?
Anyway, so here we kind of connected it really to the dialogues of a Copilot, and kind of so this is all running real code actually.
There are 36 potted
but
plants
it's
in the
an
office.
example essentially of what you could do.
Thanks. Could you please read
And
their
so
sensor
essentially
menu
here we
and
have
tell me
a
which of them
worker
are
that
low
has
on
to,
water?
in our office, we have these plants. It's actually plants as a service. So they come every week and, handle the plants and so on. And if you would add
There are 14
IoT
potted
sensors that
plants
measure
that are low on
humidity, you
water.
could actually directly send them only to the waters that week actually need new water, and so on. And so that's this scenario here visualized. And then oops. Okay, so this was not a good idea. Okay, anyway, so you kind of get navigated and you can get to that. I'll skip that. So essentially, on the one hand, scene understanding and kind of allows you to spatially ground these experiences. It also allows actually to help not only humans, but also actually robots like this one here to do their work. Oops. Let me try to correct that. Okay. Let me restart this. Share. So zoom adds another level of complexity here. So screen 2, share. Okay, we should be good to go again. So I think now the video should play. Yeah, there we go. Okay, anyways, so this is essentially a robot that then also kind of, by understanding the scene, figuring out what's where in the scene, can then carry out tasks. In this case, we asked the robot, you didn't see that, but essentially it's a demo where you can ask the robot, where did I leave my keys in what drawer? And it will kind of, just go around and open the drawers. And then in the gripper, there's actually also a camera, and so it actually takes pictures, which you don't see here, but it takes pictures and sees it there. Here, a person asked, okay, I'll just go again. Person asked if, to grab the bottle here, and then it would do that, right? Okay, so we realized actually if you want to do that, you need a little bit more. This is a preview of a paper that's that's at this conference here, where we essentially have a new task that we're trying to solve, which is in an environment, in a 3D scene, trying to predict how you should manipulate and grasp particular objects, how you should open them. So for example, a fridge, we know that if you grab the handle of a fridge, we know that it's going to be with a hinge and you have to pull it a certain way, and you kind of already do a motion that kind of compliant to what you expect, the kind of the particular door or drawer or whatever to behave. So you have expectations of how you're going to be able to manipulate that. So if we want robots to be able to manipulate environments, they also need to predict by looking at the scene, be able to predict how they should interact with those physical things like buttons, switching on the light or opening a drawer. Some doors, sometimes people also get confused and then they pull the wrong way, and then like they realize something's wrong. It all goes a lot smoother if you can predict how you should manipulate something and what are the directions of motions that you should operate. Right? So that's this work here. You would like, of course, to be able to extract a lot of information from data that's online. Here's actually some early work. Student ended up having some issues and so on. We never fully finalized this, so it's on archive. But it's essentially about grounding, grounding these kind of tutorial videos that you can find online of how to repair a car and how to do this and that, to bring all of that together in one common 3D context. So if people there's 20 videos of the same car model, car brand being repaired with different types of actions. What we did here was to ground all of that and align all of that in 3D in the same reference coordinate system. And then from the video, from speech to text and so on, extract essentially the different points of interest that they were pointing out during the actions. And so that way we could, we could ground and predict essentially where the relevant parts were in the car to build assistance. Okay, so now on to actual video recognition and activity recognition. So this was some of our early work, where what we did was from the RGB video, so in this case only a pure RGB video, predict both the hand motion, the position of the object manipulated, and the action that was taking care, and then a 3D interpretation of this. Here's an illustration of how this type of methods could be used in an assistant context where you have a step-by-step instructions for someone. As I've shown you earlier, this kind of guides where it tells you how to carry out a certain procedure, but then you have essentially, you close the loop by having the system be able to validate step-by-step, recognize step-by-step that the person is carrying out the procedure in the correct order, or in this particular example, actually does a kind of out of order, forgets a step, and then this can be corrected and addressed. Okay, so to really get to this, to these type of scenarios, we realized that we needed to collect a new type of data set, the HoloAssist data set, which was published last year at ICCV. So the key here, as we've heard, is actually difficult to figure out how to teach a person, what you can do is you can record how a person does something. But just providing that to people is not enough for, having a new person that doesn't know how to do it immediately understand, like by seeing an expert do it, that's not a great way to learn how to do it. So what we wanted to capture here with HoloAssist was how a person is being taught to do a task. Okay, so the scenario is as follows. You have a person, in this case, that wears this HoloLens device so that we can record everything that's going on. That person gets helped, as in this remote assist scenario, gets helped by a remote person. The remote person is actually the instructor that will explain step by step what to do. Now, step size might vary in a sense. If the person already generally is familiar with the task, you provide a few high-level instructions and the person figures out what to do. If the person not at all familiar with that type of task, then they might need much more fine-grained instructions. And so the goal of the HoloAssist dataset was really to capture that type of, both the people that only need high-level instructions, people that need step-by-step instructions, people that even if you give them instructions, they make a mistake, so that the instructor might have given an ambiguous instruction, the person misunderstands it, does something else, the instructor intervenes, corrects that. The goal was here to essentially capture all of that richness of kind of someone being taught how to do something. Okay? Here you see the data that we collected, and also this illustrates essentially the richness of a platform like a HoloLens, but also the RE device is capturing things very close to this and so. But the importance to actually use these type of devices as opposed to just RGB, especially at the stage where we're really trying to figure out how to do those things and what are the signals that are useful, right? So head pose, RGB, that's kind of given with these platforms. Depth camera is also there, so we can capture essentially this kind of near range depth of the interaction. We have just through APIs, we can get the hand pose also essentially all the time at 45 frames per second. Eye gaze is also provided. That's the orange vector here, which kind of indicates why the person is paying attention and allows interesting things. For example, an expert will very quickly, so normally you would expect the eyes and the hands to be focused in the same place. So it turns out, for example, that the more you're an expert, the more you're already going to lead with your eyes to the next part of the task, because you can essentially work blind. You know what to do, you have kind of muscle memory, you kind of do the task, you already look at the next thing you have to do so that you can kind of immediately go there with your hand as soon as you're done and so on. So you can kind of see very quickly level of expertise just by looking at this kind of how quickly a person looks on to the next part of the task or so, for example. So of course we capture the full audio conversation, both sides of the conversation. We have of course the IMU also as a signal. And then we also had essentially a company then make annotations, in particular, describe in detail everything that was going on, as we felt indeed the audio was not sufficient to capture all of that. So it was important to have a person look at the video, look at all this material, and then describe step by step what was going on. And so this is this interactive scenario. So you have a performer, you have an instructor, and then the instructor gets the context through the video and is explaining the person essentially what they're supposed to do. So for example, here you get an instruction. The person carries out a task, it's correct. Instructor gives the next task. A mistake happens. The instructor detects that. Then intervenes, makes a corrective, asks for a corrective action, and then this is carried out. So that's the type of things that we capture here in the video. All of this is annotated. All of this is provided essentially as additional data. To show an example, we try to go relatively broad in terms of objects. Lots of objects we could have easily in the office, like first consumer type of devices on the one hand to manipulate, and machines that we had, in a typical office environment, a few IKEA furnitures to assemble, and then a few rare objects that some of them we happen to have, like the Navi scanner is one that we actually use ourselves for ground truth in some of the stuff I showed before. Also, our guides team essentially is using this kind of quad as a prototype thing for testing some of the scenarios, so we also leverage that. Okay, so here, just I'll browse through a few of the videos here. Actually, I should go back here. These are some of the tasks that we're looking at, benchmarking, and so really provide the data set for. So it's mistake detection, intervention of the type of, so the intervention type prediction. So is it just going to be the next instruction, or is there actually a mistake happening and does it have to be corrected? Through the hand, or is it refining an instruction and so on? Predicting hand pose, where is the hand going to go next? And then, of course, at a high level, action recognition and action anticipation. Right, so here's a few kind of just showing a few examples of kind of what people were doing. So here they opened the wrong thing, kind of the type of correction that was done, and so on and so on. Right. So let me quickly skip through this. Just showing you here a few of the examples. But let me quickly go through that. There's also a number of failures there.
For action recognition, we take the action clips as input.
Then another data set that we're looking at is this is a collaboration with colleagues at APFL and with Microsoft. So here we have essentially a full exo capture. This is going to be a few hundred hours of collection. You have people that will carry out 5 different recipes. Each time they have 1 hour to carry out the full cooking kind of recipe in this kitchen. There's both healthy subjects, and then we'll also, but that probably not in the data set, collect a number of patients that have issues. I think there was 1 amputee in the data set, but then also people that have some neurological, either had a neurological event, or people that are recovering, or people that have, you know, gradually decreasing abilities. And the goal is, can you measure that? Now, of course, we don't want to instrument everybody's kitchen this way. The goal is here to have an over-instrumented kind of capture setup to learn where are the signals, you know, that we can kind of find, that we can measure, where we can much better characterize what's going on with the person at home in their kitchen, as opposed to, you know, be with a doctor, you know, once every 6 months, where they do a 5-minute kind of observation of the status of the person. So the hope is that, so we have neurologists and so on also involved in this project. The hope is that we can measure that. So lots of data being captured. So 9 external Kinect cameras measuring everything in exo viewpoints. So very strong, rich, full capture there. A HoloLens for the person himself. In addition to that, there's actually a few of the tools in the kitchen, and the doors and so on are being instrumented. In particular, the knife that people use actually has an IMU on it. And so we actually measure really that signal. So here's how that kind of looks. So here you see the person. So again, with the HoloLens, you get hand tracking, eye gaze, all of those things are built in. Because everything is calibrated here, all of this in the same continuous 3D spatial context, both with the external views and the internal views. So everything can be projected in every view. And you have, as you can see here, you see the manipulation through the IMU. You also see directly the manipulation of the knife. So you see these kind of, you know, actions of the knife hitting the board or things like this. You directly observe them also in the IMU signals. Okay. Our goal is to be able to more and more leverage all of these data that we collect, this rich data to train more generic models, foundation models. But of course, we'll never get there, you know, 100 hours at a time. The goal is going to be to combine unlabeled, unstructured videos with slightly more structured scenarios, egocentric scenarios, then with these kind of very highly annotated, multimodal, very rich data sets. But then to complement that, we also need to have synthetic data. And so this preview of work.
We introduce EgoGen,
CVPR
a generative and scalable synthetic data generation approach, specifically tailored for egocentric perception tasks.
So essentially here, the key about EgoGen, which is going to be presented, I think, on Thursday, is a collaboration with my colleague Siyu Tang at ETH, is really that this character here is driven by its own perception in the virtual world. So this is not kind of a synthetic generated trajectory in general or so. No, it's actually from the depth sensing from the observation in the scene, the character kind of essentially decides where to go. If there's multiple characters, they won't run into each other. If there's moving objects, they would kind of avoid running into those and so on, because it's essentially driven by its own perception. And if there's an object in front, they will avoid it and so on. So that's essentially something that's very scalable to generate quite rich interaction data. Of course, for now, it's just moving around the environment and looking around. The nice thing is also you can generate all of the other signals like IMU, depth camera, everything like that is also fully generated, semantics, etc. So to wrap it up, where we eventually want to go, and this is actually a project that just is starting. We have a Swiss AI initiative, and this is one of the projects within that, is to build an egocentric vision robotics foundation model. So both a model that can both interpret what's being seen from an egocentric perspective, but then also act and drive, actuators and manipulators in the scene, as you kind of see illustrated here with hand manipulation of objects in the scene. And our hope is that we can learn that from people doing things in egocentric video and so on, and bring all of this together. And as an academic institution, we're actually quite lucky that we have this supercomputer that has 10,000 H200s that's coming online now. We won't be able to use all of them all the time. This is actually the supercomputer for ETH in general. But they realized, actually based on Jensen Huang at the time, saying that this would be 7 times more powerful than in 2021 when this was released, when this was announced that the contract was signed, would be 7 times more powerful than the most powerful supercomputer back then for training AI systems. That led the supercomputing people at ETH to reach out to people doing AI at ETH to say, hey, we should do something together here. So we're very lucky. And so this is going to be quite exciting in the next few years for us to play around with this machine. This is not just 10,000 of those GPUs. It's actually 10,000 highly connected, supercomputer connected, low bandwidth, high bandwidth, low latency kind of connected, which is really the difference between a cluster and a supercomputer. Right? So we're quite hopeful to do pretty exciting stuff in a space. And I'll leave it at that. Thank you.
Okay, good. Thanks for this great talk. And okay, so we move on to the question and answer. And yeah, just go.
So great talk as always. Thank you. So I'm curious, a lot of the activity recognized
abilities to kind of to extract essentially those mid-level signals.
Data sets that have those sorts of challenges to work on.
The data sets, HoloAssist and other data sets like that have all those mid-level signals also. So you could definitely try it out there. So you could definitely leverage that and just, not start from the raw signals, but only work with those mid-level signals. Then you should be able to really train very lightweight models that are definitely real-time, even on mobile devices.
Thank you.
Thanks, Marc, for this great talk. So I just have a general question here. So you're talking about this kind of AI assistant in the future. So do you think, it's going to be in the cloud or in edge device, or it's kind of mixed, just like iPhone displays? Siri is going to be the like AI assistant at edge, and if there's difficult questions, they will send to the cloud.
Well, I think you kind of already answered it. I think what I expect is exactly as you describe it. I expect that you will want to do the simple things, you'll be able to already handle locally, and then more advanced things will be handled in the cloud. I think there will be, for some of the grounding, for some of the things, there will always be some kind of connection to the cloud, probably in most of the scenarios. And then I think, as I was describing, I think at this point, if you want a real system, I think in last resort, you still have to be able to call a person. I think like if you want really a solution that is rock solid and you can always get help, I think today you'd have these different stages still. Yeah.
Thanks.
Thanks for the talk, Professor. Really exciting work with EcoGen. Maybe you could talk a little bit about how you expect the generation of synthetic data to be used in the loop for methods in the future.
Yeah, so essentially, our goal would be to, so the problem with synthetic data is you have to feed it. I mean, you have to make it rich enough to be useful. I think so. We don't necessarily expect it to cover every possible case, but have a lot of the kind of. So I expect it to both be used to generate a lot of kind of relatively generic interaction with the environment and how, like what can happen. But there's always a problem of diversity in this data set. So you have some dimensions in which you can easily scale out diversity of the data set, but there's others in terms of, like niche scenarios and so on. Those almost have to be hand coded to kind of show up there. I hope we'll actually be able to extract some of those from real data and then replicate them in the synthetic source. So that's how I think we'll use all of this, really bring it all together. We haven't done yet. So that's what I anticipate, but let's see where we get.
Okay, so I actually have a follow-up question for the EcoGen because I'm very interested in the data quality and also data distribution. And I'm wondering, like, how do we ensure the diversity of the output data is, kind of different or basically much more diverse than the data used in training?
So the question of diversity in EcoGen is really about, what assets do you provide to the EcoGen system to work with, right? Yeah. So if you provided all types of three-dimensional environments to explore, that's on one hand, how much data you provided, what different types of data, how many environments or so. Now that's quite scalable these days. The other one is how rich is the interaction. That's something we don't have a full grasp on yet. So this is essentially a generative model of motion in the environment that's driven by the perception. We haven't really fully characterized, does that actually cover the whole richness of how a human would explore an environment? I think, essentially currently our AI character probably has its own style of exploring the environment. And so that is something that I expect that as we would really want to scale this out, we'll have to look into making that rich enough in terms of interactions and making sure it's broad enough. I think for now it explores the environment with its own special style, and so I think that would indeed be a limitation in terms of having full diversity there.
Okay, cool. Thanks a lot.
Yeah.